Isomerism, I know you have some hint as far as O-level chemistry is concerned, and this is simply the existence, okay, of compounds with the same molecular formula, but those compounds have different structural arrangement of atoms on that atom, or they have different structure formulae in simple terms. You have same molecular formula, but you have different structure formulae. Okay? So if two or more compounds have same molecular formula, but they have different structure formulae, then we say that they do exhibit isomerism. And such compounds are referred to as isomers. For instance, let's start with simple things. Let's not make life hard. C4H10. So this can be written as H3. So even if I write H3, even if I write CH3, it's all the same thing. Okay? So this is all the same thing. So it can be written this, okay? And this is butane. Or you can call it N-butane, where N means normal. So this is normal butane. Okay? Not branched, just a straight chain of hydrocarbons. But also C4H10 can mean this. Okay? Yes, if I get one methyl group and I shift it from here and I put it on this carbon number 2. Okay? Are you seeing that? And I form this. So this is 2 methyl, then 1, 2, 3 propane. This bracket is not there. Sorry for that. So this is 2 methyl propane. And it is the same molecular formula, C4H10. Okay? Now, because these two compounds, the N-butane and 2-methylpropane, have same molecular formula but different structures, then they are referred to as isomers. And so this existence, okay, of compounds of the same molecular formula but different structure formulae is what we refer to as isomerism. Let me see, somebody's outside. I don't know what he wants, but let me check on him. Just a moment. Let me pause there. Okay, guys, it's okay. It's okay. So come back. So basically that's what isomerism is about. The existence, okay, of atoms, or sorry, compounds having the same molecular formula but different structural formulae is what we term as isomerism. Now, we have types of isomerism. Okay? It also exhibits types. Yes, in O-level, that's why you stopped. You didn't talk about types. But now here, we shall talk about the types. And we shall see that there are two main types of isomerism. Okay? And each type has a good number of subtypes. And you should know, okay, all of them. You should know how isomerism can be classified. But mainly there are two. And the two types include structural isomerism, and here the difference. You have the same molecular formula, but the difference is in the arrangement of atoms in that compound. Okay? The arrangement of atoms, okay, in the compound. They are the same atoms, but how those atoms are arranged within a compound gives what we call structure isomerism. So we are going to see, don't worry, have nothing to worry about. So it's the type of isomerism where compounds differ in the arrangement of atoms within a molecule, i.e., isomers under structure isomerism differ in just the carbon skeleton. For example, the one you saw, the one we just written up, the C4H10. It can be N-butane, CH3, then CH2, and then CH3. Okay. This is propane. There is another. Or it can be 2-methyl. Okay, 2-methyl. This is CH and then CH3. So it can be 2-methyl. So if you put the CH3 here, so it can be this or this. Now, the molecule is the same. The molecular formula is the same. The molecular mass is the same. Everything is the same. But the way atoms are arranged, okay, to give the structure of a compound is different. And so that one is referred to as structural isomerism. And there are different types under structural isomerism. Then the other one is stereoisomerism. There are two main types. The first one is structure, the second one is stereo. Okay? Now here, the compounds or the isomers have the same molecular formula and the same structure formula. Okay? You have the same molecular formula and the same structure formula. But how these atoms are arranged in space, the spatial arrangement of these atoms in a compound is the one that differs. How these atoms are arranged in space, it's the one that creates the difference. Okay? And we get the differences, the geometric and the optical isomerism. We are going to see. Even under structure, we have very many, the chain, the position, the functional, and yeah, we are going to see them and what they mean. We do some examples in details. Okay? Yes. So any question as far as where we are is concerned before we proceed, before we talk about structure isomerism? Any question, you can unmute and ask. Okay, so since let's now talk about the structural isomerism, the way it is. So like I told you, with structure isomerism, you have same molecular formula but different structure formulae, different arrangement of atoms to form your structure, to form the structure. And that one is structural isomerism. And it can be grouped under chain isomerism, where, okay, they are defined. So with chain isomerism, let me see if they are, okay. Let me first give you. So the subtypes under structure isomerism. So it's okay, guys. Somebody was talking to me, so it's inevitable. So the subtypes under structure isomerism, we have chain isomerism. We have functional isomerism, and we also have position isomerism. And is there a fourth one? Maybe we shall. I don't think. Anyway, Now with chain isomerism, they differ in the chain. Okay? In the chain. For example, one might have a straight chain, another might have a branched chain, okay? But they just differ in the chain. Like the first one we saw, that N-butane and the 2-methyl, that is a chain isomerism, but the rest is the same. Then with functional isomerism, you have the same molecular formula, but you differ in the functional groups. Okay? The functional groups differ. Remember, if you started with us, the functional groups refer to that atom or groups of atoms, okay, that determine the overall physical and chemical properties of a given organic compound. So you might have the same molecular formula, same atoms, everything is the same, but the functional groups are the ones that differ. Now that one is referred to as functional isomerism. Then with position, you have the same functional group, but the functional group is on different positions. One is on carbon number 1, in another compound might be on carbon number 2, in another compound might be on carbon number 3. So the position of the functional group is the one which differs. Okay? And so because of that, then that becomes position isomerism. So that is just a hint, okay, of what we are going to talk about as far as structure isomerism is concerned. So with chain isomerism, it's where compounds differ in the arrangement of carbon atoms within a molecule, okay, and so you form different structures. Now the position of the functional group must remain the same. Otherwise, if you change the functional group, then it becomes position isomerism, not structure isomerism. For example, if it is an alcohol, you can just change the methyl groups, you change the ethyl groups to form groups, but the position of the functional group, if the OH is on carbon number 1, then it should remain on carbon number 1. Then you change everything this side. Let's see some example. For example, you can have this pentane, and this pentane can be N-pentane, normal pentane. I think I have it. Yeah, it's here. I was going to write, but so you have normal pentane, okay, the one which is not branched, okay, we call it N-pentane, normal pentane. But if I get this and I shift it from this position and I put it here, okay, that becomes 2-methyl butane. Okay, 2-methyl butane. I think nomenclature is now okay, because I've shifted and these two are different. This is pentane and this is butane with a methyl group. But also if I get this and I shift it from this position and I put it here, it still remains the same. Okay, and these two are different. This is 2,2-dimethyl propane, and this one is different from this, and this is also different from this. Okay, yes, so because they have the same molecular formula but they have totally different structures, then that one becomes isomerism. And because the difference is in just the structures, in just the carbon chain, the carbon skeleton, then that one becomes chain isomerism. Is that okay? Yes, we can name them, and if you name them, that becomes N. Hey, how can I write propane? This is madness. It is pentane. Okay? This is madness. Sorry for this. So this is N pentane, because see, 1, 2, 3, 4, 5. There are 5 carbon atoms. That was just a misspelling. Then this one becomes 2-methyl. Why 2-methyl? Because the methyl group is on carbon number 2. Okay? And then it's 1, 2, 3, 4. So it becomes 2-methyl butane. Then this one becomes 2,2-dimethyl propane. Why? Because the 2-methyl groups are on carbon number 2. So that's why it becomes 2,2-dimethyl. But if you count, it's the same structure formula. So it's the same molecular formula, but the difference is in the structure formula. So basically it is as simple as that. Now with functional isomerism, here you have the same molecular formula, but the difference is in the functional group. Okay? And remember what I told you, what I've just told you. A functional group can be an atom or groups of atoms that determine the overall physical and chemical properties of an organic compound. So you might have the same structure, so the same molecular formula, but now the difference becomes the functional group. So here they just define a functional group. For example, you're going to see such isomers also define both physical and chemical properties, obviously. If you have alcohols, such as this, can you write for me the isomers? You first write the isomers here. Yes, first write the isomers here. And see how many can you get. Oh, sorry. First write the isomers and see how many you can get. Now you can write the name in the chat box. Let's hurry up, guys. Let's hurry up, guys. So from what is given here, it is our CH. We have 2 carbon atoms and a 6. So this can be an alcohol. And which alcohol? Ethanol, as you can see. But alternatively, it can be an ether, as you can see, COOC. Okay? So this, if you count the number of carbon atoms, they are 2, and from the molecular formula they are 2. The hydrogens, they are 6, and from our molecular formula they are 6 and 1 oxygen. So it is still the same thing. So therefore this one can be ethanol. Okay? And now this one is an ether. The functional group is an ether. We shall study them when we are studying ethanols, alcohols, not ethanols. So the functional group, this C O C, it is for the ether. Okay? This is an ether. And so when you are naming it, it's a methyl and a methyl. So therefore this one becomes methyl ether. Or to avoid that confusion, then you can name it as dimethyl ether. So it is as simple as that. Can you try out this? Write all the isomers, all of them. Write all the isomers. Okay? And I want functional isomers. I want functional isomers. Let me check on your work. Okay. So it is simple. Let me show you how. So it is C3H6, and this is an alkane. You see, if you write C, it is an you cannot, if you put 3 hydrogens here and 3 hydrogens here, already 6 covered. Okay, then where we get the balance? The 2 here. So therefore this one becomes an alkene. So just put a double bond here, and then you remove one bond. Okay, and you put hydrogen here, hydrogen here, hydrogen here. Okay, hydrogen here, and then the rest is hydrogens. Okay, this bond is not there. Now this one becomes N-propene. Okay, propene. But also, if I do this, okay?
Excuse me, sir.
Yes, Edwin?
But the carbon in the middle now has got 5 bonds. Is it possible?
That's a good observation. It's not possible. It was. I was just hurrying, maybe for no reason. So one bond is not there. Yeah, even this one. So one bond is not there. That's how it is supposed to be. Thanks for that observation. So even if I do this, now you've understood once you understand that concept, carbon cannot go above 4 bonds and carbon cannot go below 4 bonds. You'll be good to go. Trust me. So this is a carbon atom. This is another carbon atom. This is another carbon atom. You can see? Okay? So this one has used 2 and also this one has used 2. So it has a balance of how many? 2 hydrogens. So put your hydrogens here. This one has used the 2, same thing. You have hydrogen here and you have hydrogen there. So the same applies to this, hydrogen here and hydrogen here. So therefore this one becomes cyclopropane. Okay? Cyclopropane. Now, why is it functional isomerism? You see, it is an alkene. Maybe let me use some different pen. It's an alkene, okay, and a propane, an alkane, okay, and a cycloalkane. You can see. So because of this, then the two exhibit functional isomerism. I hope that's okay. In case you have a question, please feel free to drop it. There is this one. You do this as homework. You do this as homework. Okay? Yes. So you can always, you do that as homework, you will inbox me with your answers. Now with position isomerism here, you have the same functional group. Okay? Somebody's calling me. Now I think they are stranded. Let me talk to him, Wanje chemu. Wanje? Kade chemu now jebaleko. I gave you some work and I hope you do the question as homework. So now with position isomerism, here you have the same functional group. Note, it's same functional group, but the difference is in the position of the functional group. Okay? Same functional group, but the difference is in the position of the functional group. Once you understand that, then you'll be okay. Compounds with the same molecular formula but defined position of the functional group within the carbon skeleton. So for example, C4H8. Can you write for me the isomers? Because you now know. Okay, you try the isomers because I might not go in the chat box to check. The answers will be there. C4H8. You hurry up. I hope you guys are done. Okay, so I'm going to do. Okay, now with this one, it can be if you write this is an alkene anyway. 4, they have this structure, the general formula CnH2n minus 2. So it is an alkene, it fits. So it can be CH3, CH2, and then CH, and then double bond, and then CH2. Now, the position, the double bond is on carbon number 1. Anyway, I think I have it. So, with this, let me first attend to this guy. Okay, Rahesh, you first sit there, I'm coming. Morning. It's how, eh? I'm coming, eh? A moment, eh? So now, the position is on carbon number 1. But I can decide to shift this double bond and put it on carbon number 2. Okay? And I form this. And this is bute pent 2 in. Not so? So that is bute. Hey, did I say bute pent? Ah, my God. What is running in my mind? So it is bute 2 in. It's bute 2 in. Why? Because the position of the double bond is on carbon number 1. I think it's because I'm attending to this. So that's the reason. But alternatively, it can be on carbon number 1. Okay? Like this. How you're seeing this. So now because the double bond is on carbon number 1. And by the for your own information, this is the same as this. Okay? Who has joined? So because the double bond is on carbon number 1, but it is the same functional group. It's the same double bond. Then therefore this one becomes butene. Or you can say N-butene, normal butene. So it is as simple as that. Okay?
Excuse me, sir.
Yes, Edwin.
Is that first example of yours safe?
Yes,
It is as if the carbon atoms in the middle have 5 bonds.
these ones, eh?
Yeah.
Yeah, good. You are good at that concept. So this one is also a mistake. Okay, let me change it from here. Let me change it now. So the concept, I always say this, if the carbon atoms within an organic compound must have a maximum of 4 bonds. If they go beyond 4 bonds, then that is no longer an organic compound, but rather your compound. Okay? Yeah, that's thanks for that observation. Now, I think I make this slide sometimes at night when I'm exhausted or sometimes, so that's the reason why even I write such. But when I'm teaching, I can't write this. I can't write such. So this is but 2 in, and this one is but 1 in. The position, the double bond is on carbon number 1, but here the double bond is on carbon number 2. But it is the same double bond. If you alternate, maybe you put a single bond somewhere or a triple bond, now that ceases from being a position isomerism, but rather a functional isomerism, because there is now a difference in the functional group. Okay? Yes. You can try this. You can try these ones. Okay? Especially. Anyway, you can try these ones. Now this is going to be homework. Okay? Here you're supposed to get 8 isomers. 8 isomers. Okay? And of 8, I think 3 are structure, 3 are position, and 3, either 3 or 4, okay, or 2 are function. So you try this and name which ones are structure, which ones are position, and which ones are function. So, but for now, you are doing these two. Do for this and for this. I want to see your answers. Chap, 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 chap. Huh? So for propan 2 or those ones, they are correct, like I told you. Oh, now when this one, let's see if they can vary. This one is going to be C. C, there are 4 carbon atoms. So if we put the Cl here, okay, that will be chlorobutane. The Cl is on carbon number 1, okay, and the rest are hydrogens, okay, the rest are hydrogens, the rest are hydrogens. If I change this Cl, okay, and I put it here on carbon number 2, okay, it becomes 2-chlorobutane. Anywhere? Can I shift it anywhere? Obviously no. So because the chlorine, the chloride atom is shifting the position, of which the chloride is the functional group here, then it becomes position isomerism. Then for this, it is CH3. CH3, it can be N-propanol, CH2, and then CH2OH. N-propanol. Or if I shift this functional group and put it here, okay, it becomes a secondary alcohol, and that one becomes propan 2-ol. That was brilliant. That was brilliant. Okay? Yes. So let's proceed to. So now that was structure isomerism. Now let's talk about stereoisomerism. You have the same molecular formula, You have the same structural formula, but the spatial arrangement of atoms, the arrangement of these atoms in space, it is the one that differs. Okay? And so that isomerism becomes stereoisomerism. And you cannot ignore it. It might appear to be some small issue, but you cannot ignore it, because it's that small issue that results into a difference in the physical and chemical properties. Let me attend. This person is calling me. Just a moment. Just a moment. Okay, it's okay, guys. It's okay, guys. So the difference is on how these atoms are arranged in space, and it results, or it gives what we call the stereoisomerism. And there are two types. One is geometric isomerism, and then the other one is the optical isomerism. This is some interesting stuff. Some interesting stuff, okay? That we should pay enough attention here. Let's talk about geometric isomerism. Now, they have same structure formulae, like I told you, same molecular formulae, like I told you, but the spatial arrangement of the groups around a double bond is the one that differs. You have a double bond, okay? Maybe this is one carbon atom, okay? And the groups behind this double bond, okay? They are the ones that differ in arrangement, okay? And the difference is what we call the geometric isomerism. Maybe, for example, and we are going to see an example down there. But the way how these atoms are going to arrange themselves across this double bond, okay, it is the one that differs. And so because of that difference, we give rise to two types of geometric isomers, as we are going to see. So a rise, it is a rise as a result of a double bond, which is banana. Now, the meaning of banana is, if we say something is banana in chemistry, it means it can be oriented within a plane. Okay? For example, how can I say your phone, okay? If I attach some particles at the corners, okay? Some substances at the corners, okay? And I put the phone on the table, and all the particles have attached on a phone lie on the same plane, then it is said to be prana. All those particles are said to be prana, okay? So even this double bond, it gives that prana, it is prana within a molecule, and this double bond does not allow free rotation of these molecules, okay, in space, okay, in that compound, unlike the double bond. So there is restricted rotation of these atoms, okay, within a compound across the double bond, okay. And so as a result, the atoms will be oriented differently in space across the double bond. And so as a result, because of this isomerism, we shall give rise to two types of isomerism. The first one is the cis geometrical isomerism. Where is it explained? Okay. Where the identical groups, the groups that are the same, are oriented on the same plane across the double bond. Okay. We are going to illustrate it. Have no worries. Have no worries. Whereas in trans geometric isomerism, the identical groups are on totally opposite planes, okay, across the double bond. I hope I have an illustration. For example, here in butane 1,4-dioic acid, okay, butane 1. Can you write butane 1,4-dioic acid? Yes, you write it. However, I want to go there to check for it, but write it. Butane 1,4-dioic acid. Are you done? Okay. So butane 1,4. I can write it as this. Let me write it for you. Normally, so that is the carboxyl group. So you have the C, then you have the CH2. It's butane, meaning those are 4 carbon atoms. You have another CH2. And then you have C. Oh my god, this is O. And then O, OH. So this is butane 1,4-dioic acid. Now, why butane? Are you seeing this? The vowel stroke consonant roll. It is followed. But otherwise it would be butanoic acid or butane and so on. So now in butane, actually, sorry, it's butene. Oh my god, I didn't see the E. It's butene 1,4-dioic acid. Butene 1,4-dioic acid. So you have a double bond here and another sorry, and another double bond here. Now, because you have a double bond, then these groups, the carbon atoms with a double bond, are here. This one and this one. Then these atoms which are attached on the double bond, they have restricted orientation, restricted movement, okay, across this double bond. And so as a result, you form such an isomer, and this is a trans isomer. Why trans? Because see, these are the atoms. This is the position of the double bond, okay? The double bond is here, okay? And these are the atoms that are attached on the carbon atoms with a double bond. So this double bond does not allow free orientation within a double bond. And so the molecule is planar. If I put the whole of this molecule on a plane, maybe on a table or on ground, all these atoms will attach on ground. That's what we mean by planar. Now, you see, the plane is this. This is one plane, okay? And this is another plane, okay? This one and this one. Now, you see, the identical groups are, you have this group and you have this group. And the two groups are on the opposite plane. You see, one is here, another one is here. You see this is a plane and this is another plane. The two groups are on totally different planes and opposite planes, okay? And since they are opposite, then this one becomes a trans isomer. And so when you want to name this, you add the word trans here, then with a hyphen, and it becomes trans but. This is A, okay? So it becomes trans butene 1,4-dioic acid. I hope it is okay. In case it's not okay, you can unmute and speak. Now,
It's not okay.
oh, Anta is here. That's good. Anta, how are you?
I'm not okay.
You're not fine, I know. But don't worry, everything is going to be fine, right? So now, like I told you, with the trans isomer or with the trans isomerism, the identical groups the groups which are the same, they are on opposite planes. So this is the first plane, okay? This side, this upper side, it is one plane, and then this lower side across the double bond, okay? So the double bond separates these groups. So this is one plane across this double bond, and then this is another plane. So the identical groups, this one and this one, they are on opposite planes, totally different planes, and they are opposite from each other. Also, you see the hydrogen. Are you seeing? Are you seeing this hydrogen? It is on the opposite plane. So as a result, they are opposite. Okay? They are opposite. And there is restricted orientation, the restricted rotation. Like this one cannot just rotate from here to this side. And the same applies from here to here. No, it is restricted. Why? Because of this double bond. But if it was a single bond, then it would just easily orient or rotate anyhow. So because they are on the opposite planes, like how you see, then it becomes a trans isomer. And so when you are naming, you add the word trans, okay? And then butene, this is butene, not A. I have a lot of things to change. Butene, then 1,4-dioic acid. Why dioic? Because you have these two carboxyl groups. So it's as simple as that. Okay? Good.
Excuse
Then,
me, sir.
yes.
Why 1 4?
Why 1,4? Because the functional group is on carbon number 1. This is the carbon number 1 and the carbon number 4, and this is the carbon number 4. So it is 1,4-dioic acid. Now you are asking sensible questions that show that you now understand the chemistry. Can you think about the other one? The cis isomer. How is it going to be? Try to sketch it on your paper. Try. Just trying. Yeah, I'm not saying you're going to sketch the right thing. Yes?
I think the functional group should be on the same side.
You think the functional group?
I think the functional group should be in the same plane.
On the same plane. So can you sketch? You sketch on your paper. You might not show us. I might not see it, but just sketch so that after you will mark yourself. Are you done? Are you done? Okay, that's pretty good. Now the cis isomer is going to be this. The identical groups are on the same plane, like how you said. So this bond is here. it is on this, not on oxygen. This one is on carbon, is on hydrogen, this one on hydrogen, this one. So they are on the same plane, like how you see. Okay, this side, all groups are on the same side. Also here, all groups are on the same side. And this one, by the way, affects the physical property and the chemical property. Because see, where the groups are on the same, on different sides, there is, if it is steric hindrance, then there is row hindrance. If you are attacking the groups, then you don't hinder the incoming reacting molecule. We are going to see all this. We are going to explain all this chemistry. But where they're on the same side, there is some degree of hindrance. Okay. Now here, actually, you can form intramolecular hydrogen bonding with this. But with this, you can. There is no way how you can form intra. Anyway, we are going to see all this. How these trans Cs affect, okay, the chemistry, the physical, and the chemical properties, okay, of an organic compound. And so when you are naming this, it becomes cis butene. This is E. Sorry for that. This is E. So it becomes cis butene 1,4-dioic acid. As simple as that. Did I give you an example? No, there is no example. Let me check the chat box. What you've been talking about. How how are we supposed to write it if it is a structure? I don't know what you are asking, but I hope your question was answered. COOC. Yeah, this was good. This was good. Now the rest was writing the isomerism. Yeah. Edwin, I like it. I like it. That's pretty good. Okay, that's wonderful. So, any question as far as isomerism, as far as geometric isomerism is concerned? Any questions for me as far as isomerism is concerned? Okay. Now let's talk about optical isomerism. It is also some cheater stuff, some interesting stuff. I hope you will enjoy. Okay. Now optical comes from light. Okay. Optical means light. So now optical isomerism, they have something to do with light. Okay. They have something to do with light. And they have the same structure formula, the same molecular formula, the same spatial arrangement of atoms. Okay? The atoms are arranged similarly. In other words, they are not structural isomers. They are not geometric isomers. In other words, they are not cis trans, but the difference is just one. Okay? Let me first talk to this guy. A moment. You, boss. Guys. So let's proceed. So now, so they have the same structure, they have the same formula, they are not geometric isomers, they are not structural isomers, but just the difference is on the, they have different optical properties. So I was attending to somebody, but he has gone. They have different optical properties in rotating a plane polarized light. Now, this is physics. This is physics. The question is, what is that plane polarized light? Now, if you have your beam of light, maybe I call the physics teacher to explain this. If you have your beam of light, okay, and you pass that beam into a glass prism, okay, into a glass prism, the glass prism is going to polarize this beam of light, okay, and the light that passes through is the one that we refer to as a plane polarized light. Okay, a prism or a glass prism, or a beam of light passing through a glass prism, the prism polarizes that light, and that light is the one that we refer to as the plane polarized light. Okay? Yes. Now, when you pass this plane polarized light onto these optical isomers, okay, they do rotate a plane of polarized light in two different orientations, either to the left or to the right. Okay? So for any optical isomers to exist, they must have, okay, before this I haven't talked about this. So they do rotate the plane polarized light either to the left or to the right. Are we together? And so you have the same atom, same molecular formula, same structure formula. You are not a geometric isomer, but the difference is just rotation of this plane polarized light. And so because of that, we have two isomers. Okay? And these isomers are usually mirror images of the other. Are we together? They are usually mirror images of the other. And the isomers include the D isomers and the L isomers. Or you can say the dextrorotary isomer and the revelatory isomer. Whereby the D isomer rotates this plane polarized light to the right, and the L isomer rotates the plane polarized light to the left. Okay? And they are mirror images of the other. For example, you can have this. This is lactic acid, which is 2-hydroxypropanoic acid. And that is your lactic acid. Okay? 2-hydroxypropanoic acid. Now, you can write it in this format. You can write it as this. The CH3, the H, and then the functional groups here. Now, if I take the mirror image of this lactic acid and I do this, just get the mirror and insert it here. Can you write the mirror image? Try to write the mirror image. Maybe let me give you some few seconds. Get the mirror and put it here and write the mirror image of this. Let's hurry up. Uh-huh. Have you finished writing the mirror image? So yes, that's good. So the mirror image is going to be that one. And when I was teaching, some students insisted that even I write this as, but anyway, that's how it is. So anyway, that is the mirror image. And so these two images become the isomers. Okay? Where this one, it's the D isomer. Okay? Because it rotates the plane polarized light to right. However, there is no way you can show that. And this one becomes the L isomer. Okay? So it's just a mirror image. Okay? A mirror image of the other. So basically it's as simple as that. Any questions for me? You can write that. You can write the mirror image of that. Are you done? Yes, I hope you're done. And the answer here is, so that is the D isomer. And the mirror image, which is OH, you can see it here. H, you can see it here. So this becomes the L isomer. So basically, it is as simple as that. Any questions for me?